In this video, I'll be looking at section 4.4 problems on Achieve with you. Please remember 4.4 is looking at the second derivative test. That's going to determine the concavity of functions when functions are concave up and concave down. The first problem, there's really no work to do. It's just a logical thinking problem. They give me a graph that looks like a portion of a quadratic function. So I went ahead and just graphed it here on my paper so I could think about it. And I can say, well, this looks like y equals x squared that's been shifted. It looks like 2 units to the right and 1 unit down. We know it crosses the x-axis at the ordered pair 1, 0. And I made the assumption that the vertex was at 2, -1. Doesn't matter, because I know that the derivative of any function that's going to have that shape is going to be a linear function. It would be continually decreasing before it gets to 2, so it would have a negative slope before 2, and then it would have a 0 slope at 2, and then it would have a positive slope after 2. So I know the derivative is negative before it gets to x equals 2, and it's positive after x equals 2. Now, since the derivative is itself a linear function, you can say, well, then that derivative has constant slope. It's always increasing. It's going to have a slope of approximately 2. That's what I did right here for my f prime of x, or sorry, for my f double prime of x. Now, I'm supposed to use these graphs and this logic to determine what happens at 1 in the original function and in the first and second derivative. So I did that. I can easily look at f of 1 on the original function, and clearly it's an x-intercept. We know f of 1 is 0. Now, if I look at f of 1 on the derivative, and even if you didn't draw it out, you know f prime of 1, or I'll say you should know f prime of 1 is negative, because the slope is the derivative. And you could say, well, the slope of that function, it's a negative slope since the function is decreasing. So I am unequivocally certain that f prime of 1 is negative. And I can also say I am certain that f double prime of 1 is positive. How am I supposed to know it's positive? Well, because I can look at the function and I can see it's concave up. Anytime it's concave up, the second derivative is positive. I could also just look at my graph of the derivative and say, well, your derivative, it starts out negative, then it's going to have an x-intercept at the minimum point of x equals 2, and then it's going to be increasing after that. So that derivative is always increasing. It always has a positive slope. Thus, the second derivative is always positive, certainly still positive at x equals 1. So that tells me that f double prime of 1 is positive, f of 1 is 0, and f prime of 1 is negative. Now, on mine, they ordered it like this, to where you just had to show that the derivative evaluated at 1, which is the negative here, clearly that's less than f of 1, which is 0. And then, of course, that is less than f double prime of 1, which is some positive number. And you can see that that's precisely how it was entered in here on Achieve. Now, most of the problems in this section have us working out stuff. These first two are more trying to be thought-provoking questions. I don't like the way that they worded the statements in the second problem, but we can get around that. So here's what it's talking about. It gives you a graph of some, or very basic graph of some function, and it says that this function represents profit over time. So my horizontal axis is representing time, my vertical axis is representing profits. So now, obviously, if you look at this, you say, well, hey, this is good. Now, what I would also want you to do is say, well, this is part of a U-shaped function. So not only is it increasing, but it's also concave up. So yes, it's increasing, but the rate of increase is also increasing. So we can say, yes, profits are increasing. So at profits, when this began, the profits were positive, but the profits became even more positive as time goes on. So yes, the slope is certainly positive. So the profits are increasing with respect to time. But then more importantly here, the second derivative. Since the slope of this, notice the slope here at the beginning, it's not as steep as the slope at the end. Both are positive, but the slope here at the end is steeper than the slope here at the beginning. Well, that tells you that not only are the profits increasing, but the rate of increase of the profits is increasing. So that's what I put here in my statement. Profits are increasing and the rate of increase is increasing. So you say, well, this is an extremely good scenario for this business then, because hey, everything's going great. And as time moves on, it's just getting better and better and better. So I know that my first and second derivative are equal to 0. It just became a matter of trying to figure out which of these wordings fit that scenario. And really by process of elimination, I knew which ones that it couldn't be. So the first one, business has been picking up, okay, but now it's cooling off. No, that makes no sense whatsoever. We're losing money. No, they're not. We're doing well. Okay, but our growth rate is leveling off. No, it's not. The next one, we're losing money. No, you're not. Business had been cooling off. No, it was always going up. So the only one that comes remotely close is this third one. The outlook is great. The growth rate keeps increasing. Everything true in that statement. And that's the only statement where everything is true. Now we go through several problems where we just work out the second derivative test. So notice on these, it'll give you the function. In this first function, I have a cubic. And it's going to ask you for the intervals on which the function is concave up and which the function is concave down. Now, you'll see that this number 3, it took me 2 attempts on. And the reason it took me 2 attempts is I didn't read my directions very well here. Normally, and for most of the problems in this assignment, when they ask for the points of inflection, they only want the x value. On some of the problems, and I think maybe 3 or 4 at most, they will want the ordered pair for the point of inflection. So once you find the x coordinate for the point of inflection, you have to plug that x coordinate back into your original function to find the y value at the point of inflection. That's what I didn't do in my first attempt on this problem. It wasn't that I made a mistake, it's just I didn't do that part. So please keep in mind, when they want a point of inflection as just an x value, and if you just gaze above where they do point of inflections, you can see the little parentheses with the asterisk, comma, asterisk telling you that they wanted an ordered pair, an x and a y value. So now let's talk about how this problem is worked. I'll go ahead and maximize this screen. So for this problem, I had my 8x cubed minus 5x squared plus 5. Obviously, I need to take the second derivative. So first, to take the first derivative, power rule tells me that it's 24x squared minus 10x. I take the derivative again, and I'll get 48x minus 10. Now, when I take that 48x minus 10 and I set it equal to 0 and think, why would you set the second derivative equal to 0? Well, that's the only place that your possible inflection points could occur. Now, why do I call them PIP for possible inflection points? Because not every time your second derivative is equal to 0 are you going to have an inflection point. Most of the time you do, but not every time. So I have to say, well, the only way that an inflection point could occur is when the second derivative is equal to 0 in this problem. So I do that, and that's going to give me 48x is equal to 10. And then x is going to equal 10 over 48, which reduces down to 5/24. So then my second derivative test tells me that I need to break up the domain of the original polynomial, which is negative infinity to infinity, with this possible inflection point at 5/24. So I go negative infinity up to that possible inflection point, and then from that possible inflection point to infinity. We choose test points within each of these regions. I chose 0 for my first region. I chose 1 for my second. Now, we plug those test points into our second derivative. It is the second derivative test for concavity. And I didn't need to factor this one. Most of the time, I'll put it into a factored version of the second derivative, not necessary here. So then I can say, well, all right, when I plug a 0 into that expression, clearly I'll get a negative 10. It's a negative. When I plug a 1 into that expression, I'll get 48 minus 10, positive 38. And remember, we don't need the 38. We only care that it's positive in that region. For any region where a second derivative is positive, your function is going to be concave up shaped. I always think of it as it's going to look like a portion of a U. It could be the entire U, or it could be the first portion of it, or it could be the second portion of it. But no matter what, it's concave up in that region. For that first region between negative infinity and 5/24, we see that it's going to be concave down. And then keep in mind, like I said, this problem also asks for the ordered pair of the inflection point. So once I determine, yes, 5/24 is a point of inflection. How do I know that? Because my curve changed from a negative second derivative to a positive second derivative. So 5/24 is a point in which my graph changed from being concave down, and then at 5/24, it changed to concave up. So I can say, all right, it changed concavity at that point. It is an inflection point. Let's go ahead and find the y coordinate at that point. I just plugged it back into my original equation, and I got of course, I used my calculator, 4,195 over 864. So I can say my point of inflection is this ordered pair. And you can see I had to go in and enter the information into Achieve just like this. And please remember, on some of these screens, you may have to scroll down to get to all of the questions asked. Number 4 here should be just like it. Yeah, gives me another polynomial function. Now, please notice this time it only wants the x value of the point of inflection, and then when it's concave up and when it's concave down. So my work for that, I went in and I said, well, all right, I'll take my 8x to the 5th power minus 3x to the 4th. The derivative is going to give me 40x to the 4th minus 12x cubed. The second derivative, now notice I'm not setting my first derivative equal to 0. I'm not trying to find when this curve has a maximum or minimum point. I just want to know inflection points and concavity intervals. So I take the second derivative. In this case, 4 times 40 gives me 160x cubed. Then I'll have minus 3 times 12 for 36x squared. At that point, I know I need to factor that second derivative so I can set it equal to 0 and find my possible inflection points. I do that. I can say, well, I can factor a 4x squared out of these terms. When I do, the first term will be left with a 40x, and the second term, if you factor a 4x squared out, you'll still have a minus 9. Now, the zero product property tells me if I set these two factors equal to 0, either the first factor equals 0, which gives me x is 0, or the second factor is 0. When the second factor is 0, I know 40x is equal to 9, so x is going to equal 9 over 40. Now, these are my two possible inflection points. Now, honestly, I already know that the first one is not going to end up being an inflection point. And I would like for you to know that too. If you were thinking about the graph of the second derivative, yes, it's going to have an x-intercept here and an x-intercept here. At this x-intercept, it's going to cross. At this x-intercept, it's only going to touch. At any x-intercept that it just touches, your second derivative is not going to change sign there. So if it's negative before, it's negative after. If it's positive before, it's positive after, which means my original curve does not change concavity at 0. I am certain of it. Now, I'll go ahead and use my formal second derivative test to show that, but I know this one's not a critical point, this one is. Let's show it. So you break up the domain of the original function, which is all real numbers, with these two possible inflection points. So I say, well, negative infinity to 0, then from 0 to 9 over 40, then from 9 over 40 to infinity. Now I choose test points within each one of these regions. Please notice -1 is in the first region. I can say the second region, 9 over 40, that's like 0.225. So 0.1 is certainly in there. And then from 9 over 40 to infinity, I chose 1. Now I can say, all right, I need to plug each of these test points into, I would prefer to plug it into the factored version of your second derivative. And notice how I said the 0 that came from the 4x squared, I said, that's not going to be an inflection point. This is going to show you why. That factor that created that x-intercept, or that zero for the potential inflection point, it's never going to cause a change in the sign of your function, because no matter what you plug into that factor of 4x squared, whether it's negative 1.1 or 1, it's always positive. It's irrelevant to the sign of the product. So I can say, well, the second factor is going to change sign. Yes, it will cause a concavity change. So I'll have a concavity change at 9/40. Now, when I start plugging values in, you plug the -1. You'll get -49. It's a negative. When you plug a 0.1 in, you get 4 minus 9. It's -5. When you plug a 1 in, you'll get 40 minus 9. It'd be a positive 31. So in our first region, we're going to have a positive times a negative. We know our second derivative is negative in that region, which tells me that my original function is concave down in that region. In the second region, we still have a positive times a negative. So my graph did not change concavity. My curve is still concave down. And then in the third region, you have your second derivative is positive, which means your original function is concave up. Now, when you're asked about your concave intervals, I could see someone saying, well, why can't I just say it's concave down from -infinity to 9/40? These points where the second derivative is equal to 0, they're either a point where it changes concavity, or it's a point where the graph is instantly concave neutral just for an instant. So you'd say, no, 0 cannot be included in the region that's concave down. It's concave down from -infinity to 0, and then it's concave down again from 0 to 9/40. Then it's concave up after that. So I can say, all right, my concavity intervals, I would have to say -infinity to 0 union 0 to 9/40, and then concave up from 9/40 to infinity, and my only inflection point is at 9/40. Now, please notice that's precisely how I entered in the information into Achieve, and please make sure you see that you have to list those two regions that are concave down separately. You can't say, well, since it's concave down before 0 and after 0, why can't I just include 0 in the concave down region? Because it's not concave down at 0. At that instant, we would say it's concave neutral. Now, for number 5, same type of problem. We are given another polynomial function. This one, they're just asking us where it's concave up and concave down. They don't even ask us to list the inflection points this time. No problem. So here's my polynomial, 12x squared plus x to the 4th. I take the derivative, I get 24x plus 4x cubed. I take the second derivative, 24 plus 12x squared. This one's easily factored. You can say, well, you could factor a 12 out of both of those terms, and when you do, you'll have a 2 plus x squared left over. Now, while that was easily factored, it's important to remember it does not further factor. Sum of squares is not factorable in the real number system. So you say, okay, I'll just have to leave the 2 plus x squared alone, which now, and again, if you tried to solve that, you would get, well, 2 plus x squared is equal to 0 when x squared is equal to -2, which is not possible. So this tells me that the second derivative cannot equal 0. All that means is that there's no inflection points. If there's no inflection points, then that just means it has the same concavity everywhere. So I can still do my second derivative test. What is the concavity? So I can say, well, my only interval is from -infinity to infinity, and my test points, I just plugged in a 0. It's clearly in that region. Plug that into your second derivative. Clearly the first factor would be positive. Your second factor is always positive. So you say, well, if you're going to have a positive times a positive, your second derivative is positive. All that means is that this function is always concave up. The second derivative is always increasing, which means you know that this function has to start off decreasing really rapidly, because that first derivative has to continually increase as it moves on through this. So it starts off decreasing rapidly, then decreasing slowly, then flattening off, then slightly increasing, then increasing a little more quickly, then forever and ever increasing more quickly, because that second derivative is always positive. Pretty cool question there. Sometimes the easy questions like that can be more confusing than the more difficult ones. Now, number 6. Want to look at this one with you, and you can see that in this problem, we had our function written as a product. I went ahead and just made it easier by saying, instead of leaving it as a product, why not go ahead and distribute that out? And that way you won't have to use the product rule to take the first and second derivative. So I distributed the x through this group, and it gave me x squared minus 7x to the 3 over 2. And now achieve is the one who gave me that restriction that x has to be greater than 0. Notice that was their restriction there. Because if I were just looking at this, I would say, well, I know that x has to be greater than or equal to 0 because I have the square root of x in there. But they're saying, nope, it's not even equal to 0. It's strictly greater than 0. So we have to keep their restriction in mind. Now, for the first derivative, once you distribute out, it's easy. You just say, well, it's going to be 2x minus 21 over 2 x to the 1/2 power when I use the power rule on that term. Now take the derivative again. Derivative of 2x is 2. I bring the 1/2 down, multiply this, and I'll get minus 21 over 4 x to the negative 1/2 power. Now I know I need to set this second derivative equal to 0, so I was thinking it'd probably be easier to think about setting it equal to 0 if I went ahead and rewrote this back into radical form. So I have 2 minus 21, and this is divided by 4 on the root of x. You need to understand this is the square root of x in the denominator because of that negative. So now I can say, all right, I need to solve for x when I set this equal to 0. Best thing I can do, especially since this is being subtracted, is let's add it to both sides. That'll give me 2 is equal to 21 over 4 on the root of x. I multiplied both sides by 4 on the root of x to get 8 on the root of x is equal to 21. Now I know I can't solve for x as long as it's inside of a square root. So what I did next is I just squared both sides. 8 squared is 64. The square root of x squared is x. 21 squared is 441. So 64x is 441, x is 441 over 64, and Achieve is wanting exact answers, so no need to put that as a decimal. Now, I have my 441 over 64. I went on up into my problem, and here's where I had to remember, and I made a mistake initially. I had to remember this problem starts at 0. It's not like my other problems that started at negative infinity. So I start at 0, I go up to my critical point, 441 over 64. Then I go from that critical point up to the end of the domain, infinity. I chose a number between 0 and 441 over 64. 1's easily in there. And then a number between this and infinity, I know 10's easily in that region. 10 would be 640 over 64. So these two test points fit the regions. Then I plug those test points back into my curve. When I do that, if I plug the 1 in, I would get 2 minus 21 over 4 times 1. That's just 2 minus 21 fourths. Clearly, that's going to be a negative number. 21 over 4 is, you're subtracting 5.25 there. So I get a negative. In my next region, I have 2 minus 21 over 4 on the root of 10. I know that that root of 10, it's greater than 3, so that denominator is greater than 12. 21 over a number larger than 12, that's not going to be greater than 2. So I'm saying 2 minus a number less than 2. I know it's positive. I would rather you do these without needing to plug them into the calculator. Logic should dictate it, but you can plug into the calculator if you prefer. Now, anytime my second derivative is positive, your original function is concave up. Anytime it's negative, your original function's concave down. Then my inflection point was at 441 over 64. You can see that I entered this information in to Achieve, and that's all they wanted. They wanted, and again, they only want the x coordinate for the point of inflection, and then the concave up and concave down interval. For number 7, Number 7 is, yet again, a problem you could have done like I did the last one, where you say, well, it'll be easier if you go ahead and distribute in the first step. And it might have been. I didn't choose to do that in this one because I knew that the derivative would be so easy anyway. So just like the last problem, you could have went ahead and FOILed it out and then just used the power rule. I chose to keep it as it is and use the product rule when I take the derivative because I knew the derivative of the first was just 1. And I said times the second plus the first times the derivative of the second, which is going to be your negative 3x squared. At this point, you still have to distribute out. So you'll have 1 minus x cubed, and then I'll have minus 3x to the third and plus 24x squared. I collected like terms. I wrote it in descending order. Negative 4x cubed plus 24x squared plus 1. Now, my second derivative, I just used the power rule on that polynomial, and I'll get negative 12x to the second plus 48x right here. Now, I know in order to find the possible inflection points, I need to set this second derivative equal to 0. So I factored it. I can easily factor out a negative 12x here. When I do that, I'll be left with a positive x and a minus 4 inside the group. Zero product property says negative 12x is equal to 0, which gives me x equals 0, and x minus 4 equals 0, which will give me a solution at x equals 4. Now, these two are my potential inflection points. I break up the domain of the function, and since the function was just a polynomial, its domain is negative to positive infinity. So I can say, all right, I'll go negative infinity to the lower potential inflection point, that lower potential inflection point to the higher, and then of course the higher potential inflection point to infinity. Now I choose test points within each of these regions. Negative 1 is in the first region here, 1 is easily in the second, and 5 is in the third. I plug these test points into what I have here as the factored form of that second derivative. So I can say, well, what happens when I plug a negative 1 into this expression? Well, negative 12 times a negative 1 is a positive. Negative 1 minus 4 is a negative. So I know I'll have a positive factor times a negative factor. That's a negative. My region is going to be concave down over that region, or my curve is going to be concave down over that region, negative infinity to 0. Then when I plug in a 1, your first factor now is going to be negative instead of positive. Your second factor is still negative, but we know a negative times a negative gives us a positive, and f of x is concave up whenever the second derivative is positive. And then my last region, I plug in a 5. Well, negative 12 times 5 keeps that first factor negative, but 5 minus 4 is going to make that second factor positive. Anytime we have a negative times a positive, second derivative is negative, original function is concave down. So then I can say, I know that my function is concave down from negative infinity to 0, union 4 to infinity. It's concave up from 0 to 4. And then this is another one of those problems which wanted the ordered pairs for your inflection points. So I knew, hey, both of these potential inflection points were actual inflection points. So then I had to go back into my original function and plug in a 0. When I plugged in a 0, it's kind of easy to do just like this. You can say, well, you know, it's going to be negative 8 times 1. So f of 0 is negative 8. My ordered pair is 0, negative 8. When I plugged in a 4, you get 4 minus 8, which is negative 4. And then it would be 1 minus 4 cubed. That's 1 minus 64. That gives me a negative 63. 4 times 63, 252. My inflection point, the ordered pair 4, 252. And please notice whenever you list those multiple points of inflection, you have to put them in ordered pairs, of course, and put a comma between each two. So don't try to use the union notation like you do for interval notation down here. It's a comma up here, unions in the concave down and concave up interval notation regions. Now, number 8. Number 8 is giving us our first problem that's looking at a quotient, and we just have to make sure to answer all of the questions. So I went ahead and did a second derivative test so I could clearly answer those questions. And I said, well, all right, here's my quotient here. I know I'll have to take the second derivative, the first derivative. So I would bring the denominator up to the numerator, but times the derivative of the numerator, which is 0. So all of that first term is 0. Then you say minus the numerator 1 times the derivative of the denominator. That's derivative of x squared is 2x. So clearly that first derivative is just going to be a negative 2x over that denominator x squared plus 10 quantity squared. Now we take the second derivative and you say, well, every time you take the derivative, you're going to square the denominator. So now it's to the fourth. Bring that denominator up to the numerator times the derivative of the numerator. Well, the derivative of negative 2x is negative 2 minus the numerator, negative 2x, times the derivative of the denominator, derivative of any group to a power, the power comes down in front, times the group x squared plus 10 to the one lower power, times the derivative of what was inside of that group. So you can't forget the chain rule in this problem. Derivative of x squared gave me the 2x on the end. Now I can say, okay, now I'm set with that, and I'm simplifying in this step. So what I did to simplify from here to here is I said, please notice in your numerator, this term has an x squared plus 10, this term has an x squared plus 10. Let's take out that common factor of x squared plus 10, reduce it with one of the factors of x squared plus 10 in the denominator. That's why from this step to this step, you see x squared plus 10 to the third in the denominator. Now in the numerator, your first term, it's still going to have one factor of x squared plus 10, but that's easier to work with because you can then distribute the negative 2 through that group and you'll get negative 2x squared minus 20. That's where that came from. Now, when you factor the x squared plus 10 out of the second group, it's gone. And you'll just have 4x times a negative 2x. That would be a minus 8x squared. You're subtracting that minus 8x squared. So you say, well, okay, that's just going to become a plus 8x squared. 8x squared minus 2x squared gives me 6x squared minus 20 all over that denominator. Now, the only thing I had to do beyond that was I factored a common factor of 2 out of the numerator. It can't cancel with the denominator, but can make it the numerator look a little bit better. And I can say, well, my second derivative is going to be 2 times 3x squared minus 10 over x squared plus 10 cubed. Now, think about that denominator, x squared plus 10. You have an even function plus a constant. If I ask you to graph x squared plus 10, you'd say, well, that's just a parabola that shifted up 10 units. Yeah, it can never have a negative value. So I am guaranteed the denominator of this second derivative, it's always positive. Clearly 2 is always positive. So if I said, well, then when is the second derivative going to be positive? You'd say, well, it's positive as long as this 3x squared minus 10 term is positive. That's what you need to take out of this. So once you factor this, you say, well, since every other factor in here is positive, I know this second derivative is positive if the term 3x squared minus 10 is positive, because 3 positives would make a positive. Now, if 3x squared minus 10 is negative, my second derivative is going to be negative and my original function will be concave down. That's all the information you need to answer the questions. So please remember, the factor of interest here was 3x squared minus 10. So they try to confuse me by putting 3x squared plus 10 in a lot of the options. I can say, nope, okay. The function is concave up whenever 3x squared minus 10 is positive, because that's going to make the second derivative is positive. It's concave down whenever the factor 3x squared minus 10 is negative, because it would make your second derivative negative. And then you can say the values at which the inflection points occur are the same as, well, remember, the inflection points are going to be when the second derivative is equal to 0. The second derivative can equal 0 if and only if 3x squared minus 10 is equal to 0. And so they're just saying, well, it's the zeros of 3x squared minus 10. That's where your inflection points will be. Gorgeous. Now, the next problem. You're thinking, well, if that one was gorgeous, how can we get to a better one? The last one was a nice one that we used the quotient rule on. Well, this one is even more nice because we're bringing in exponential functions. We have f of x is equal to 2x times e to the negative 7x. This is another one of those problems where they're wanting the point of the inflection as an ordered pair. So I have to find the x value, and then if I determine that it is an inflection point, after I do my second derivative test, I have to plug it back into the original problem to solve out. And then, of course, I have to give my intervals of concavity, concave up and concave down. Let's show the work for this one. Whoa, let's show the work not sideways. So here's my f of x. We have f of x is equal to 2x e to the negative 7x. I take the derivative. Remember, product rule required here. Derivative of the first function, well, derivative of 2x is 2 times the second plus the first, 2x, now times the derivative of the second. And be careful here. Derivative of any exponential function is that exponential function times the derivative of its exponent. Well, the derivative of negative 7x is negative 7. Now, you would be wise to go ahead and factor this before taking the derivative again, or else it's just going to get messier and messier. So when I looked at this, I said, well, in the first and second term, they both have a factor of 2e to the negative 7x. I can factor that out. When I factor that out, what are you going to be left with? Well, in the first one, you're going to have a 1. And in the second term, if you factor out the 2 and the exponential function, you'll have an x times a negative 7, well, minus 7x left over. So this is my factored version of the first derivative. I don't want to set that equal to 0. I'm not solving for critical points or anything, but still so much better to work with this than what I had prior when I take the second derivative. So now when I take the second derivative, I can say, all right, I'll still have to use the product rule. Derivative of the first, derivative of any exponential function is that exponential function times the derivative of its exponent times the second plus that exponential function times the derivative of the second. But the derivative of 1 minus 7x is just a negative 7. Now I look at all of this expression and I could see students struggling to factor this correctly, but I need you to. So whenever you look at this, you should be able to say, well, your second term has a factor of 2 times negative 7 times this exponential function. Your first one has all of that too. 2 times negative 7, well, that's going to be negative 14 e to the negative 7x. I need to factor all of that out. Now, when you factor all of that out, you say, well, what are you left with? Well, in this first one, you would have 1 minus 7x. And in the second one, here's where I could see students making a mistake. They say, you don't have anything left. Yes, you do. Whenever everything always factors out, you have left a 1. So you can say, oh, then what's left is 1 minus 7x plus 1. Yes, gorgeous. So you have a factor of 2 minus 7x left for that second term. So I can say, okay, now zero product property tells me if I want to set this second derivative equal to 0, then either the first factor equals 0 or the second factor equals 0. I know the first factor can equal 0, and I can show myself that if I just say, well, it's the same thing as negative 14 over e to the 7x. You can't divide negative 14 by any number and ever get a 0. So I can just say, well, my first factor cannot equal 0, pure and simple. What about my second factor? It can certainly equal 0 when 2 is going to equal 7x or when x is equal to 2/7. So I'm confident that my one and only potential inflection point is at 2/7. So then I can say, all right, then I will do my second derivative test, break the domain up negative infinity to 2/7, then from 2/7 to infinity. I choose test points, 0's in the first region, 1's in the second region. Now I show my factored second derivative, and I went ahead and wrote the first factor as negative 14 over e to the 7x times the factor 2 minus 7x. That first factor, you know it's always a negative. Negative 14 divided by any exponential function, it's always going to be a negative. So I just said, well, that first term's guaranteed to be negative. The second term is what's going to determine the concavity because it has a sign change. We can say when we plug a 0 in here, 2 minus 0 is going to be a positive. 2 minus 7 times 1, that's 2 minus 7, it's a negative. Anytime you have a negative times a positive, we know that our second derivative is going to be negative, which means your original function is concave down. Anytime you have two negative factors, you know your second derivative is going to be positive and your original function is concave up. So once I saw that, I can say, well, clearly, then 2/7 is a point of inflection. The curve is concave down before, concave up after. Now I just need to take this 2/7, plug it back into my original function. I did that right here. 2 times 2/7 times e to the -7 times 2/7 power. That's -7 times 2/7. The 7's cancel, and you just have, well, that's e to the -2. So I get 4/7 e to the -2 for the y value. I went ahead and wrote my inflection point as the ordered pair 2/7 and then 4 and 7, or 4 divided by 7e squared. That just looked better to me. You could leave the 4/7 e to the -2 if you preferred. But you can see this is the way I entered my information into Achieve, and Achieve liked it. For the last problem I'll do in this video, and then I'll do the remaining problems in a second video, let's look at number 10 together. So number 10, it's similar. I like it because it's bringing up logarithmic functions. We had exponentials in 9. Why not throw logarithms in 10? Now, anytime you bring in logarithms, Achieve should not have had to tell us x has to be greater than 0. They did, but we should have known that with or without Achieve telling us that. We know that logarithms only exist for values to the right of the y-axis. They asymptotically approach the y-axis. So you can say, well, of course, x has to be strictly greater than 0. Now, when I take my derivative of 5x squared, 10x. Derivative of the natural log of x, 1/x. Now, when I take the second derivative, first term's easy. You just say, well, it's just 10. The second term, when I took the derivative in my head, I thought of that second term as x to the -1. So when I take its derivative, the -1's going to come down, and then I would have x to the -2. -1 times x to the -2 is better written as -1/x squared. That's what I did. So then I can say, well, I need to set that second derivative equal to 0. I can do that by moving the -1/x squared to the right-hand side and then solving for x. We can say, well, let's multiply by x squared on both sides. Then I would divide by 10 on both sides, and I would get x squared is equal to 1/10. So x is equal to the positive or negative square root of 1/10. But, and I didn't mean for my voice to crack there, but we know the x value has to be greater than 0 because we have logarithms in the original problem. So that negative possible inflection point, I have to ignore it. So you say the only possible inflection point is the positive square root of 1/10. And then I just said, well, I know that the square root of 1 is 1. So I brought it up here and I just said, I'll go from 0 to my potential inflection point, which is 1/√10. And then from that potential inflection point, 1/√10 to infinity. A number between 0 and 1/10, 1/10's inside there. And then between 1/10 and infinity, I chose 1. Nothing special about these values other than they are certainly within the region they're supposed to represent. Now, when I plug these into my second derivative, that first one would become 10 minus 1/1/10 squared. Well, 1/1/10 squared, that's going to become 1/100. That makes that second term 100. 10 minus 100, negative. Now, of course, it's a -90. I don't care about the 90 part. I just care that the second derivative is negative in that region. When I plug the 1 in, that becomes easy. You just say, well, that's going to be 10 minus 1/1, which is going to be a positive 9. So my second derivative is always positive in this region, always negative in the first region. We can say our curve is concave down from 0 to 1 over the root of 10, concave up from 1 over the root of 10 to infinity. Yet again, it wanted an inflection point, and it wanted the exact value of the inflection point too. So you say, well, you just plug your inflection point in to find the y value in the inflection point. And you can say, well, that's going to be 5 times 1 over the root of 10 squared plus the natural log of this 1 over the root of 10. Now, when I solved this, I said to myself, well, I know if I'm squaring this, 1 squared is 1, the root of 10 squared is 10. So this is 5 times 1/10. Gives me 5 over 10. 5 over 10 reduces down to 1/2. And then I said, well, this second term plus the natural log of 1 over the root of 10. So I just thought, well, I know that that 10, it's to the understood negative 1/2 power. So you could have looked at this and said, well, that's plus the natural log of 10 to the negative 1/2. What did I do with that negative 1/2? Same thing I can do for every logarithmic function. I can bring it down, that exponent down as a coefficient. I can say, well, that becomes minus 1/2 the natural log of 10. To me, that just looked better. You could have left it like that, but this looks better. And then I can say, all right, then my inflection point is that 1 over the root of 10, and then the y value in exact form is 1/2 minus 1/2 natural log of 10. And you can see that that's precisely how I entered it in to achieve. This time they switched it up and wanted the inflection point last and the concave up and concave down intervals first. All right, guys, I'll stop with that for now, and I'll do a second video for problems 11 through 16.